Hello, how are you doing? I hope you are doing good. So, let us continue with our discussion on mitochondrial toxicity by different xenobiotics. In my last lecture, I told you different ways, different mechanisms by which a xenobiotic can disturb the structure and function of mitochondria. And one of those mechanisms was that a xenobiotic can interfere with the protonophoric activity of the mitochondria. You see, mitochondria has got a very important function to perform, and that is done by a mechanism, and that part of mitochondria which perform is known as protonophore, and that protonophore is responsible for transporting the protons across the intermembrane space. I told you mitochondria has got two membranes. One is outer membrane, another one is the inner membrane. So there is a trafficking of molecules from the outer membrane is permeable to many molecules, whereas the inner membrane is impermeable. But there, how then the molecules will enter into the matrix, they will enter through the exchange of the protons. So that is called as protonophoric activity. So many of the xenobiotics, they disturb the mitochondria by disturbing the protonophoric activity that you should underline. I give you one example of a drug. This is the pentachlorophenol. Pentachlorophenol is a fungicide. It is used to eradicate, to treat the fungicide infection. And PCP, we call it as PCP. It is also used to remove the fungus from the wood. And this pentachlorophenol is also the metabolite of many pesticides, and this pentachlorophenol produces or changes the internal environment of the intermembrane space. It makes it a little more acidic. When it enters through the outer membrane and goes to the intermembrane space, it changes the pH of that space. It produces acidity, and that acidity disturbs the transport of the protons. And this is one mechanism by which the function of the mitochondria may be affected. This we call as protonophoric activity, and the pentachlorophenol is the best example. So you know that this will disturb the protons. It brings those protons back into the matrix. They should go away from the matrix, but due to a disturbance in this acidic environment, it brings back those protons to the matrix, and then those protons are able to cause they change the inter membrane potential, the electric gradient there, and they lead to toxicity. So this is one way by which the xenobiotics can enter into the mitochondria, and they disturb the structure and function of the mitochondria. The second mechanism is this protophoric activity is also responsible for the uncoupling of oxidative phosphorylation. And due to that uncoupling of oxphos, I told you in the last lecture that there is something like oxphos. So that oxidative phosphorylation is disturbed, and that results not in the production of energy which a mitochondria should do, but it results into the formation of the heat. Many of the drugs, they cause their toxicity by disturbing oxidative phosphorylation. We study oxidative phosphorylation in our lab regularly, and basically in the liver or kidney, and we find that many of these drugs, they are affecting oxidative phosphorylation. That is through the effect on proteinoperic activity. In nature, what happens is, in spite of energy, the hibernating animals, through hibernation, during the hibernation period, they produce no energy, but they produce heat because they want heat. So a disturbance in the hibernating animals, lizards, the frogs, the snakes, in winter season they hibernate, and when they hibernate, they don't eat anything, they don't perform any activity, but they are alive. So, how they are alive? In spite of producing energy, they are producing heat. So, that is the enthalpy increases. That is how the mitochondrial function, from producing energy to producing heat, has been done. The second mechanism of mitochondrial toxicity is very important, and that second mechanism, inhibition of NADH production. You see, NADH is a reducing equivalent. It is responsible for producing the molecular oxygen changing into water. It changes molecular oxygen into water. So therefore it is called as the reducing agent. And that reducing agent, NADPH, that is inhibited by many of the drugs, many of the chemicals. And the books and the literature shows that there is a inhibition of the formation of ATP. There is the inhibition of ATP synthetase. The ADP plus P do not produce ATP molecule, and that is because of the disturbances in the citrate cycle. The citric acid cycle is disturbed, and therefore there is no production of ATP molecules. That is through affecting. This is a very, very common mechanism. Many of the drugs, chemicals, they affect the NADH production, right? So this is one of the mechanism by which the mitochondria may be injured. The third mechanism, which is very important, is the inhibition of the fatty acid beta oxidation pathway. Inhibition of the fatty acid beta oxidation pathway. Beta oxidation pathway is responsible for changing fatty acids into acetyl coenzyme A, and acetyl coenzyme A is required in the mitochondria for, that acetyl coenzyme, I told you that it is required by the citrate cycle. So the acetyl coenzyme A, how it can enter, or how these xenobiotics they can enter, they need a transporter, and that transporter is carnitine. And see, these xenobiotics, they affect the carnitine, they affect the transporter carnitine molecule. And this is exemplified by a very good example, and that example is valproic acid. Valproic acid is an anti-epileptic drug, epilepsy, mirgi. So valproic acid is given to the patients suffering from epilepsy. But this valproic acid has been found to be toxic to liver. It causes steatosis. It induces, it affects that steatosis, and these impairments are caused through mitochondria, and there is inflammation in the mitochondria. Mitochondria get inflamed or swelling. In other words, we can say that the mitochondria, they get inflamed. So this is how the valproic acid, a well-known epileptic drug, is affecting the mitochondria. How it can do that? They affect the beta oxidation pathway. That is, they affect the fatty acids. They affect the acetyl coenzyme A, and this anti-epileptic drug is not allowing the acetyl coenzyme A to function, and the result is the swollen mitochondria. It happens in the matrix. it goes all these carnitine molecule and acetyl coenzyme A. You remember when we were talking in the last lecture the function of acetyl coenzyme A. So it leads into the swollen, the inflamed mitochondria. There is another very good mechanism, and that mechanism is accumulation of these acetyl coenzyme and others. They lead to the reactions, and the next is the sometimes the xenobiotics that are entering into the mitochondria work as a pseudo substrate. There is a substrate, and if the substrate mimics some chemical mimics the substrate, it becomes a pseudo substrate. So you know that there is something like acetate in the citric cycle. Acetate with the help of acetyl coenzyme A is changed into oxal acetate, and this oxal acetate with the help of an enzyme aconitase changes into isocitrate, and then this isocitrate changes into alpha glutarate. This is the basic mechanism of the citrate cycle or the citric acid cycle, or in general you call it as Krebs cycle. So there is a substrate acetate. Acetate is worked upon by acetyl coenzyme A. Acetyl coenzyme A changes into the oxal acetate. Oxal acetate changes into citrates with the help of aconitase. It changes into isocitrate, and then we get alpha ketoglutarate at the end product. What will happen? If some drug is able to mimic the substrate, say for example, I can quote fluoroacetate. Fluoroacetate is a rodenticide. Fluoroacetate is a rodenticide. It was discovered after World War II. And this fluoroacetate serves as a pseudo substrate. It is not acetate, but it is serving as, it is posing as if it is substrate. So it is, when it goes to mitochondria, it changes into fluoroacetyl coenzyme A. In spite of acetyl coenzyme A, there is the formation of fluoroacetyl coenzyme A. Then the oxal acetate, and in spite of the citrate, we get fluorocitrate. See, every story has changed. In spite of that, we get fluorocitrate. And this fluorocitrate, the matter ends there. There is no formation of the alpha ketoglutarate, and there is no formation of the NADH. There is no formation of NADH. So when there is no formation of NADH, then what will happen? Then it will be called as, if the NADH formation stops, say for example in the cell, what will you call it? You will call it as a very good phenomenon. You should remember these 2-3 words. As I told you, I can ask you what is protonophore, what is aconitase, what is the function of acetyl coenzyme A, what is the oxidative phosphorylation, what is beta oxidation pathway, and similarly there is something like lethal synthesis. You must have heard about it, and if you have not heard about it, you should remember this particular term. We call it as lethal synthesis. What does that lethal synthesis mean? The lethal synthesis mean that there is, due to some disturbance in the mitochondria, there is no production of the reducing equivalent NADH. And if there is no NADH, what will happen? The molecular oxygen will not be changed into water, and it will lead to oxidative stress, or it will lead to oxygen toxicity, right? So mitochondria, I told you that mitochondria performs many functions. The inner mitochondrial membrane, the intermembrane space is playing a pool where many things come out, many things go in, but many things are not allowed to enter into the matrix. If they enter into the matrix, they will disturb the enzymes of the matrix, and they will be responsible for the release of the cytochrome C, and that cytochrome C will be released through the mitochondrial permeability transition pore. So if anything goes wrong with the gradient of the matrix, or if anything goes wrong with the inner mitochondrial membrane, it leads to opening of a pore, and that pore is called as mitochondrial permeability transition pore. And when that pore opens, the cytochrome C comes out, right? The cytochrome C comes out. So in this way, we discussed three basic mechanisms. One, that what is the effect of a xenobiotic on the protonophoric activity of the mitochondria. Second, what is the effect of xenobiotics on NADH production? And third, that is the on ATP synthesis. And third is inhibition of the mitochondrial fatty acid beta oxidation, that is the inhibition of the acetyl coenzyme A. Acetyl coenzyme A means the disturbance in the citric cycle. And the third mechanism that we discussed was the xenobiotics, they served as pseudo substrates. Then that is the mechanism when we call this as pseudo substrates. So now we are left with other mechanisms, that what will happen if the accumulation of the xenobiotics or drugs or the cationic xenobiotics occurs in the matrix. What will happen if the electron transport chain is inhibited? What will happen if the inhibition of ATP synthetase activity is occurred? Then what will happen if the binding of the xenobiotics to the cardiolipine occurs? What will happen if the lack of oxygen is there in the mitochondria? So these are some of the points that we are going to discuss, because it will take a long time to discuss, and it will be difficult to upload the entire lecture on YouTube. So I'm taking the liberty of teaching you slowly, and that is, we discussed basically three mechanisms today. One is effect of xenobiotics on protonophoric activity with the help of the pentachlorophenol as the example, the effect inhibition of the NADH production with the help of valproic acid, and then the what will happen if the substrate is not there but there is a xenobiotic which serves the purpose of a pseudo substrate, that is fluoroacetate. So remember pentachlorophenol for first step, remember valproic acid for second step, and remember fluoroacetate for the third step. We shall discuss more. Maybe it may take one or two more lectures to study this effect of xenobiotics on energy disturbances, and for that we have to study only the mitochondria. So keep pace with me. I'll be teaching you a few steps in the next lecture. Thank you for watching.